In this video, we're going to look at implicit differentiation in a much more complicated looking relationship, one that is definitely not a simple parabola or circle or any nice geometric shape. We have x cubed plus 2x squared y plus sine of x times y. We don't have any sense looking at this immediately what this graph would look like, but we will still be able to get a formula for slopes. So let's go through that process. What we're going to find out is it doesn't matter how complicated you make this expression, you can always get to dy dx in a fairly straightforward way using our approach of taking the x derivative of both sides. So we're going to take the x derivative of everything on the left-hand side and taking the x derivative of everything on the right-hand side, which is a little simpler. Let's do the right-hand side first because it is so simple. The derivative of 1 with respect to x is just 0 because 1 is a constant. The left-hand side is a little hairier. Let's go term by term because we can differentiate sums term by term. And I'll be explicit again about taking the derivative of the inside each time. So the derivative of x cubed with respect to x is 3x squared dx dx. Then we have here, we have a product. We have 2 out front, and then we have the product of x squared and y. So let's take the derivative of the x squared. That'll be 2x dx dx times y. Derivative of the first times the second, unchanged. Then plus the first unchanged times the derivative of the second. And again, remember, we're taking the x derivative of y. That's just dy dx. First times the derivative of the second. And it turns out we're going to need more room for this, so let's move that over. And now we take a look at the sine of x times y. So plus, we plus in the derivative. The derivative of sine anything is cos of the same thing. Then we multiply by the derivative of the inside. So we have the derivative of the inside, but the inside is a product again. So being careful. X is our first term. We'll get dx dx times the second, which is y. And we're going to need even more room. So we'll move this to the next line. So we'll have dx dx times y plus x unchanged and the derivative of y with respect to x. All of that equals 0. So as long as you're careful and methodical about taking your derivatives, there's nothing new here except the treatment of the y variable. And it's exactly what it should be when you take an x derivative. Derivative of y is dy dx. Once we've done that derivative calculation, we can tidy up a little bit. And we notice that dx dx is just 1. And then we can expand these a little bit better. Here we have 4xy's plus the 2 applies inside here, so we get 2x squared dy dx. And then we get the cos of xy times dx dx is 1 times y plus the cos of xy times x dy dx. All right. What you notice, if we go back to what the question's asking, is we're looking for dy dx, and you think, well, if I tried to solve for x or y in this equation, that would be really hard. But if we're solving for dy dx in the derivative, it turns out not to be that hard at all, because dy dx just pops out as a multiplier. And so what we can do is gather terms really easily. We gather all the terms with dy dx and put them together, and that's going to let us solve for dy dx without too much trouble. So dy dx is in several terms. Specifically, it's in the 2x squared dy dx, and it's also in the x cos of xy. And then we have all the other terms. We have the 3x squared, we have the 4xy, we've already got that term, and we have the cos xy times y, and the right-hand side is unchanged at 0. Once we've gotten this far, we can now hone in on the dy dx. We'll copy this over to the next page to give us a starting point. So continuing this calculation, dy dx times 2x squared plus x cos of xy is going to equal the negative of all this other stuff. So negative 3x squared, negative 4xy, negative y cos of xy. And just to save some time, I'll scratch that out and put it underneath as we divide through by that term from the left-hand side. And that would be our formula for dy dx. Notice how complicated it is, but if we know what x and y are, then we can get the value of the slope at any point. Now let's take a quick look at the question that was asked in this page. Is the point 1, 0 even on this curve? Imagine trying to draw this complicated relationship. It's hard to even guess where to start, but if we can find one point, at least then we might have some ideas. Well, this is a checking question. Is the point 1, 0 on this curve? Well, what that would mean is that when we plug in x equals 1 and y equals 0, do we get this equation satisfied? Well, the left-hand side is going to be x cubed, 1 cubed, plus 2x squared times y, 2 times 1 squared times 0, plus sine of x times y. That's going to be 1 plus 0 plus sine of 0 is also 0. That's going to equal 1. Perfect. The right-hand side, no matter what, is equal to 1. These are equal. So the point that we used, 1, 0, is on the graph. So with that in mind, without knowing the whole shape of this graph, we can use this information about slope to tell us something about the graph, at least around the point 1, 0. In pictorial form here, let's draw our graph. Let's call that the point 1. We know the point 1, 0 is on this graph, whatever it looks like. But we also know a little bit more, because we know dy dx is equal to that expression from the last page, which we'll fill in here. With that formula, we can sub in the point 1, 0 and find the slope at that location. That'll give us negative 3 times 1. As soon as you see a y here, it's a 0, so minus 0. And 0 times anything is 0. And on the denominator, we'll have 2 times 1 plus 1 times cos of 0. That'll take a bit more thinking. Cos of 0 is actually 1. So at the end of the day, we'll have negative 3 over 2 plus 1, which is 3. Oh, that's a nice round negative 1. That will be the slope on the graph. This graph here, this complicated graph, we can't really imagine, but we do know that at the point that we've looked at, the slope will be negative 1 at the point 1, 0. So what we can imagine is, just connecting that down, this is going to be the tangent line to the graph. Don't know much else about the graph, but it's going to look something like this, at least in the neighborhood of the point 1, 0. We can use that idea to then estimate some values, like moving back a bit. What would the point on this complicated curve be approximately close to 1? Let's say at the point x equals 0.95. Well, for that, we can use our tangent line approximation, which would be given by y equals our slope, negative 1, x minus 1 plus 0. That's our slope. It's the multiplier of the x, and that's our x naught or a value, and this is our y naught or our c value, whichever nomenclature you like or notation you like. This is building up our tangent line formula based on 3 ingredients: the slope and the x and the y coordinates where we're starting or referencing ourselves. And we can tidy that up as negative x plus 1 if we like, or if you like 1 minus x. With that, we can make a prediction. The tangent line y value at x equals 0.95 is going to be y equals negative 0.95 plus 1, or positive 0.05. Now if we're talking about on the graph, the y value is going to be approximately 0.05 at x equals 0.95. Just because this is the tangent line, it's exactly on the straight line here, but the graph might deviate a little bit in one direction or the other, and so we're just estimating the value with the straight line approximation. In this case, the words around the statements are quite important in terms of interpreting whether we're talking about the tangent line itself or on the curved graph. We can take this one step further here using some technology and actually get a computer to generate the graph of that complicated relationship. Notice it has asymptotes, it has sort of wavy behavior from the sine of x times y here and here, but if we focus in on the point 1 and 0, notice that is on the graph here, and we zoom in to the point 1, 0 here, we can actually see that it's fairly smooth there. When we look at the zoomed in version, we can get a slope line drawn in, and that was the slope line that we found of -1, and it matches the graph here from the computer-generated image perfectly, as we would expect because of the process that we used to get to this value. So this tangent line graph, which was y equals -1, x minus 1 plus 0, that defines this green line. It is a perfect tangential match to the quite complicated graph that was defined by our original function, this complicated cubic combination with sine of x and y. So again, a very powerful technique to be able to take complicated expressions and still get the slope at any point if that's what we need.